Yes, Oishi, Halima, am I audible to both?
Yes, ma'am.
All right. So, till two properties we have done, no? Just check what all have you written. Halima, you were there. Oishi, you were also there, no? In the magnetics class. Just
Yes.
check. I think till two properties only you all have written, or per could we do? Because this is empty.
We did this part.
You did?
We did this part.
You did this part? No, till which property? What was the last thing that you have written?
Yeah, we just finished that previous thingy. We're just starting again.
This one was written properties you did not write?
No.
Okay. So copying part you can do later. Let me discuss the other two properties also. So properties of, we are studying bar magnet. Let's complete a major portion of this. Most of the notes I've pre-written for you because time will be wasted. So the other theory I have written it, origin of magnetism and all. So it won't take time. So let's complete this chapter also. So first property was the attractive property. Attractive property means north, north, south, south means the like ones will repel each other. North, south will attract each other. Then we have the directive property. Directive property means freely suspended string will be there. You tie up a bar magnet, north-south polarity is there. Okay. And then what you will notice, automatically the magnet will align itself from the north to the south direction like this. Okay. Then we have the other about the magnetic monopoles. See, when we talk about the monopoles means when you have monopoles means that you have the single polarity species. When we talk about the monopole, this is about the single polarity species. Single polarity species. Now, single polarity means, like if I talk about electrons, they are completely negatively charged. Or if we talk about protons, they are only positively charged, right? And they exist also. They independently exist also. Okay. Now, see, in magnetics, let's say this is a north pole. This is a south pole. Okay. Now, what happens is if I break this magnet, what will I obtain? On this end, I'll obtain the north polarity, and on this edge, I'll obtain the south polarity. But this is actually not possible. Like, even if I break this into two parts, monopoles cannot exist in magnet. You can't have north polarity just existing or a south polarity. You can never have a bar magnet. This is north pole. This bar magnet is north polar, north pole, or this is just south pole. What will happen even if I break it? This part, the leftover part will develop the south polarity, and here this leftover part will develop north polarity. Definitely length of the magnet will reduce because we have cut it into half, but the polarity is like you can never have a polarity like this. North can never exist, or a polarity like this, south can never exist. So north and south will automatically exist. We'll do EMI chapter. There also we'll see. We'll have loops present on all the sides of the loops. We'll notice the polarities will exist automatically on the opposite side. So monopoles cannot exist. Mono means single, poles means polarity, and we are already done with the monopole moment and all. Last property is about the magnetic induction. Magnetic induction means, let's say I have an iron ball with me. What is this? This is an iron ball. Okay. Now let's say I have a magnet present, north south magnet, bar magnet present. Now what do? I rub this iron ball continuously on this bar magnet. Okay, I'm rubbing it. After a certain time, I'll notice that this develops slight magnetization by itself. which is nothing but temporary magnetization. Temporary magnetization. Okay. So property to induce magnetism in magnetic substance, that is known as magnetic induction. We are inducing magnetism to objects. So some materials have this tendency, like bar magnets have the tendency to magnetize. That is known as magnetic induction. And the substances that take up these substances are known as ferromagnetic. We will be talking about all these substances also. They are ferromagnetic substances. So these are the four basic properties of a bar magnet. Now we'll see some terms related to the bar magnet. That will more or less complete it. Then the numericals part will be left. Okay. So please start writing from here. We class certain terms related to magnets. First is magnetic polarity. Now, magnetic polarity, you already know. What kinds of polarities are there in magnets? Two kinds. Magnetic polarity means a north polarity and a south polarity. Next term is magnetic axis. Magnetic axis means if you draw an axis from north to the south pole. It's an imaginary line. This is not really existing on a magnet. But see, for our convenience to plot things, to calculate magnetic field, axis is required. So this axis is known as the magnetic axis. Okay, magnetic axis is a line passing through the south and north pole. Now, if we have magnetic axis like this is the magnetic axis. If you take up a perpendicular line to it, on the bar magnet, if you take up a perpendicular line to it, that is the magnetic equator. Okay, this is a magnetic equator. Fine. A magnetic equator is what? It is a line passing through the center of a magnet perpendicular to its axis. So magnetic equator and magnetic axis are, why are they helpful for you? To identify whether it's axial case or equatorial case like your electric field. Last is magnetic length, means length of the magnet. You just take the separation from the extreme edge of north and the south pole. That gives you the magnetic length. This is all in the theoretical part of bar magnet if the question comes. Now we'll move on to the numerical, but I'll be discussing the electrostatics part together with you. Okay, because it will give you a revision also. So I hope you all must be knowing that. And then that's in that way we'll come to the numericals also. That will complete this topic. This is there. It's a very small, short chapter. Please write it. Have you understood the theoretical part, properties and the terms, Halima and Oishi?
Yes, ma'am.
Okay. Okay, let's compare the electrostatics one with this. There's a concept of magnetic charge. Now, magnetic charge is actually not a real thing that is existing. Electric charge is there, which is a real thing that is existing. So, two kinds of electric charges are there, plus Q and minus Q. Okay, SI unit is coulomb. This we already know. Write it in the same manner in your notebook. When you will write, make it in a tabular form, comparison of electrostatics and magnetostatics. There's a concept of magnetic charge. Concept of magnetic charge basically means we know the intensity of the magnetic charge. It's not real thing we know. There is a north polarity and a south polarity. Then coming to electric dipole. Electric dipole is charge multiplied to the separation between them. Right? So here the magnetic dipole. Magnetic dipole has the formula magnetic charge into the separation between the north and the south pole. One more formula we already know for magnetic dipole is area into the current. Okay. Then we have electric field on the axial line. So see electric field, yes, this you all tell me. What's the formula for electric field on the axial line? 2 kp by r cube. Okay. And direction is same as that of electric field. Okay. Then we talk about the magnetic dipole. Magnetic dipole, just write the same analogous form. See, what is this? This can be written as 2p by 4 pi epsilon naught r cube. Okay. Magnetic dipole will be, see, 2, 2 will come. A will be here. Electric dipole moment will become magnetic dipole moment by r cube. So K's value here is mu naught by 4 pi in magnetism. So we'll write mu naught by 4 pi r cube. This becomes the formula for magnetic. Direction is same, but as that of the magnetic field. Same thing will come over here. Okay. Then we talk about the equatorial point. In equatorial point, electric field is equal to minus Kp by r cube, right? And when we talk about the direction, it is opposite to that of electric field, right? So here also we write the same analogous form. There is a magnetic field. Oh, I have written magnetic moment here. This is minus K by r cube. Now K is minus mu naught m by 4 pi r cube. Just remember the electrostatics part and make the analogous here. Same thing, but with the magnetic field. Now torque is, tell the formula of torque at least. We studied in electrostatics.
P into PE sine theta.
P cross E. Yes, PE sine theta, which is P cross E. Here the torque will be, see, this will be M cross P, and this we have studied also in the previous chapter, M cross B, MB sine theta. So same thing. Last is the work done. Work done means, let's say we have a dipole. Plus Q is there, minus Q is there, okay? When this rotates, let's say this is some theta 1, this is some theta 2, okay? So here the work done that we have studied, that was minus m dot b cos theta 2 minus mb, in fact, not m dot b, minus mb cos theta 2 minus cos theta 1. This was equal to the work done as well. Now, if the angle was 90, means only one angle was given. We used to write minus m dot b, which was equal to minus. Sorry, this is electrostatics part. No? This will be p pe cos theta 2 minus cos theta 1. So we used to write p dot e minus pe cos theta. Here it will be mb. Like if there is a bar magnet. Just a second. Okay. Let's say here we have a bar magnet present. So this bar magnet now rotates to theta 1 or theta 2. So this work done will be equal to the potential energy, that is minus mb cos theta 2 minus cos theta 1, which will be equal to minus m dot b, which is equal to minus mb cos theta. Okay. Like this, it's very easy to remember the magnetostatics part. Okay, so if you, that's why I told you in the starting, only practice electrostatics properly, electric potential properly, your other chapters will be secured. This is just exactly what you've studied in electrostatics. It's advisable, practice electrostatics properly. This will be done very clearly, but write it properly. Okay, please start writing, then we'll practice few numericals from this. See, like this, we have two bar magnets. Let's say this is the first one and this is the second one. So, yes, tell me for the first one, is the point P lying on the axis of it or equatorial point to it?
Axis.
Axial. So whenever you extend the magnetic axis. For magnets also, you extend the magnetic axis and see like this. So axial means it will be in the same direction. Okay, so north to south. So this is how we'll have. Let's say this. This is B1. And for the second magnet,
Equatorial.
equatorial. Very good, Oishi. This is its axis. So at this point P, this is in the opposite direction. So north to south will be below. This will go up. This is B2. Now see value of B1. B1 is axial. So it will be mu naught M by 4 pi R cube into 2. 2 K M by R cube. And direction of this is minus I cap. Okay. B2 will be, see, this is equatorial. This is minus, but minus sign is for the direction. Take the magnitude, mu naught M by 4 pi R cube. This will be J cap. Now see, when you put in the values, the net value will be given by under root of B1 square plus B2 square. Now these kind of questions we have done a lot in the previous chapter. Okay, that's why. This one also let's do. After that, yeah, we'll discuss something else. First write this, then let me discuss the next question. This you can solve later. Okay, see, this says that show that motion of a bar magnet in uniform magnetic field is in SHM. Now see, for SHM to occur, if we talk about the linear motion, this is from your class 11th. The force is equal to minus k of x, where we say force is directly proportional to the displacement from the mean position. Okay, but if it is rotational, anything is rotating. If it is rotational, torque is equal to minus k theta. Okay, tau is directly proportional to theta. Now, see, here if I talk about the torque, we know tau is equal to m cross b, which is equal to mb sine theta. Now, a bar magnet can't rotate much under the influence of a magnetic field. The angle is very small. So we can almost write, see, when I say small angle approximation, this means theta is almost greater than or equal to, not greater than, less than or equal to. Theta is less than or maximum it is equal to 15 degrees, not more than that. That is what, when you can apply the small angle approximations, okay? And second is, in this case, your sine theta almost becomes equal to theta and your tan theta almost becomes equal to theta. When we did the ray optics chapter, I think that time we have discussed this point. So anyways, right now what you can say, tau is equal to mb theta. So this shows that torque is directly proportional to theta, which satisfies the fact that yes, it is under SHM. But further, if the question can be modified, like this is a question from the board's paper, but if modification or one or two more steps can come, that is C. K's value from here will be MB. Omega is equal to under root K by I, where I is moment of inertia. So you can write this as mb by I. Now, once you know omega, you can say linear frequency is equal to omega by 2 pi. Okay, so this will be omega is this. So this will be 1 by 2 pi under root of mb by I. Okay, so this is the extra part. If it comes, you can use this. And then again, if the time period is asked, time period will be 1 upon frequency. Like this, you can keep on elaborating the portions. So write it down, then we'll discuss now a theoretical part. In numericals, you don't have much apart from this, okay? Write it first.
Theta is less than or equal to 15 degree.
Yes, it is less than or maximum equal to, like, if I say sine 7 degree, so answer will be almost equal to 7, like 6.9 something. So theta, sine theta and the value of theta, they are almost the same, or tan in fact. Okay.
Yeah.
You see, like we discussed about the electrostatic field, electric field lines, we have the concept of magnetic field lines. So, see, the way we had electric field lines representing the electric field, similarly, magnetic field lines are also imaginary lines that represent the magnetic field. But there are certain differences and certain similarities. Imaginary lines drawn in the region of magnetic field to represent them. So let's come to the properties. Magnetic fields do form closed loops. See, we have a positive charge, we have a negative charge. What did we study in electrostatics? We studied that for the positive charges, the field lines are away. For the negative charges, the field lines are coming towards it. So these are forming these aren't forming complete closed loops, right? The field lines are coming from the positive, ending towards the negative. We often use the term terminating, originating from the positive, terminating towards negative. Exact term in your NCRT is terminating. They don't form any closed loops, right? But in magnetic field, what happens? From the north to the south, outside the field lines flow. But inside the magnet, the field lines do flow from the south to the north pole. Okay, so like this, a complete closed loop is formed. North to south, outside, and inside, south to north. So this forms a complete closed loop. Okay. Second property is, like we discussed, tangent to the electric field line will give you the direction of electric field. Similarly, tangent to any point on the field will give rise to the magnetic field. And this also we discussed in electrostatics, wherever the field lines are located closer to each other, that represents a stronger electric field. Similarly, here also, wherever the field lines are located close to each other, they represent stronger magnetic field. Okay, and wherever we have gaps, so magnetic field is weaker. Like here, region 1 will be greater than region 2. Next, we have two magnetic fields cannot cross each other. This was there in electrostatics also. Means, see, if I take two tangents, for two tangents, what will happen? One point will have two tangential points. Means one point is giving two different directions. That's not possible. So that's why we say magnetic field lines also do not cross each other like the electrostatic field lines. These properties are similar. Closed loop property was completely different. Now, the number of field lines is directly proportional to the pole strength. If you have a very stronger magnetic field existing, lots of magnetic field lines can be drawn. So when you want to represent a greater number, this is there in electrostatics also. When you draw a large number of lines, that shows a greater strength. So here, since closed loops are formed, you form the rings. Okay. Last property is this: when you have straight parallel lines equidistant to each other for uniform. Like if I have B1, B2, B3, B4, B5, all these straight lines are present, all of these will be equal to show the uniform magnetic field. So you draw straight, parallel, and equidistant lines. And if you want to represent it for the non-uniform one, the gapping will be different. The one will be greater. They can be in any direction, inclined, meeting, non-parallel to each other. Are all these 6 properties clear to both of you?
Yes, ma'am.
Okay, so how much time is 55? Just take the screenshots of this. Please write it in the next class. Write it, and in the next class, what I'll discuss with you is just the last part is left, the matter part. Okay, you take the screenshots first.
Chinese fluorophore. Okay, ma'am. Yeah, ma'am.
Okay, then class, just one last class is left for this topic. So on Wednesday, we'll complete this chapter. Okay, all right, then. Thank you.
Ma'am,
Yes, Halima.
how many backup classes are left for?
See, one for this chapter, then EMI few classes, AC few classes. From where have you attempted, Halima? Directly from Ray Optics, no? Or did you take any classes of EM waves too? I think your complete first book is left, no? So yeah, few classes will be required. In November we'll go with this. Although I'm trying to quickly complete it. Till fifth chapter, it will be done by this month. So other three chapters will be left. So the EMI and EM waves are very short. A little time will be taken in AC. Okay,
I was there for EMS, ma'am.
waves you
Right.
were there.
Yeah.
Complete chapter.
Yes, ma'am. Even I wrote the test on.